Morning. I'm Nadya Mason. I'm the Interim Vice President for Science, Innovation, and Partnerships at the University of Chicago, as well as Dean of the Pritzker School of Molecular Engineering, and a quantum physicist myself. So it's an especial pleasure to welcome you to today's briefing on quantum science and technology. We are in a defining moment for American leadership in quantum, where our ability to develop quantum information technology is now a driver for economic growth, cybersecurity, and global competition. Today, you're going to hear from leaders in industry, academia, and government who are going to highlight for you what's happening in the field, outline where we go next, and discuss partnerships and why investments are so vital in this moment. I first want to thank the other universities who helped organize this event with me. Purdue University, the University of Wisconsin-Madison, University of Illinois, Urbana-Champaign, and Senator Durbin for hosting this event. So to start, please join me in welcoming the President of the University of Chicago, Paul Alivisatos.
Thank you, Nadya, and thank you all for being here. It's so wonderful to see this incredible turnout. And I think the turnout is here because there's a sense amongst all of us that America and the American people have a special moment to see the development of a new kind of technology, a technology that will have extraordinary impacts. And you want to know more about it if you're not the sort of person who studies superpositions and entanglements and quantum operators, but you want to understand a little bit more about where are we and what would this mean. And I think many of you will be able to remember the moment when you first saw the large language model AI type of tools do something that astonished you. And it happened kind of all at once. This was something that was percolating and people were talking about it and there were AI winters. And then suddenly many capacities came together and there was an inflection point and things really, really took off. And that's the topic of today's discussion, is to explain that we are in a situation today where we know that there's something truly transformative possible in the area of quantum technology, with the ability to achieve more control over the microscopic energy evolution inside quantum systems. It will be possible to make extraordinary breakthroughs in communications, in cryptography, in quantum computing, but also in areas like medical imaging. It won't be a universal computer, I think you'll hear about that, but in certain areas of application, optimizing supply chains or transportation networks and delivery systems, it will have an outsized role that will really transform certain fields and make opportunity possible in ways that today we really don't have anything quite like that. I want to especially talk for a moment about the ecosystem aspect of this, because if there's one thing that over many generations now America has proven itself to be extraordinary at, it's creating a kind of ecosystem for going after a problem like this. So here today, we have a group of universities from the Midwest that Nadya just mentioned. In our case at the University of Chicago, planning for today started 20 years ago. When we first started to make our plans for hiring faculty, creating the infrastructure, and building out systems. But along the way, we partnered with other universities nearby who are also here, and it's been a deeply collaborative activity. But more importantly, it's been a deep cooperation with the two local national laboratories, Argonne and Fermi. And it's been a deep cooperation more and more every single day, more so with many leading companies and small companies that are being fostered in the area and that are all coming together to do something that none of us could do alone, but that requires the partnership of all of us. And I think there's a kind of genius in the American system for science and innovation that brings all of those partners together. And when we get that right, the accomplishments are absolutely extraordinary. I think that's the moment that we're at right now. We have that possibility in quantum. It's a technology that's going to have enormous impact. There's nobody better that I could now turn it over to than to the next speaker, Paul Dabbar. Paul, am I okay on timing? Or I see Nadya looking at her watch and thinking, it's okay? Okay. Or should we wait? So Senator Young is coming, and we're trying to time his arrival with our handoff here. That is, well, handoff, okay. So, Paul, when I just talked about this ecosystem, here's a leader in our society who has lived in all the different parts. The Navy, he worked for a little while at Johns Hopkins and did research in applied physics, so he's been in that world. He was really senior figure at J.P. Morgan. He was deputy undersecretary for the national labs and knows the national labs like nobody else. He's had startup companies and played roles inside fostering tech ecosystems. Who else could there possibly be who could be as special to be as the deputy secretary for Commerce, Paul Dabbar? Paul.
Well, thank you. This is, I think, a great overview of people from industry who I know well, and from academia who I've been engaged with for quite a bit, and policymakers here from the Hill about both from the past of how we kind of got to where we're here today and where we're going to the future. I want to talk a little bit about kind of how we got here in the recent past, and the building blocks to lead into what we're thinking about, I think giving a little bit of a teaser of what we're thinking about for the administration and the work that we're doing. We're moving forward on science and technology heavily. Yesterday was a big footprint on AI. There was a series of executive orders dealing with an overall set of where we're going with AI. There was one on AI infrastructure. And I have an academic lecture on the 8 drivers of location selecting for data centers, if anyone's really interested in my academic papers, as well as very commercial efforts on supporting exporting of AI and data centers, where America's leadership on that. It wasn't that long ago that and Paul was talking about this. That these things kind of came to be in the national lab complex and American innovation in the private sector. I'll just give the AI supercomputing, since it has to do with UChicago also, and as well as Urbana-Champaign on high performance computing. It was only around 2016 that the GPU was first used in a high performance computer. Anyone know where that was done first? It was done at DOE, and it was at Oak Ridge National Lab, and it was called Titan. It was right after that the IBM machine was built at Summit, which was the first #1 computer to use a heterogeneous GPU, CPU machine, regaining Americans' leadership in high-performance computing. And in 2020, when the future Undersecretary for Science, Dario Gil, and I, when I was Undersecretary for Science, did an interview with the Wall Street Journal in April of 2020, we talked about how AI for biotech drug discovery was going to show the way towards therapeutics associated with the COVID topic. And we got to that in 9 months versus 4 years. And why did that happen? It didn't happen because the testing phases went faster. It was because high performance computers built by IBM, built in conjunction with DOE and the national labs with AI, shine the light of which ones were the high probability, and that led to 9 months versus 4 years. So the advancement of technology is not only theoretically possible, it actually happened, and most people don't realize that was possible. And in that interview that Dario and I did in April of 2020, we got up and we said, look, we could actually do this. And it was in the Wall Street Journal. You know how many phone calls Dario and I got after that? Zero. No one paid attention to us. Now everyone said, like, oh, of course, you could use AI and supercomputing for biotech drug discovery and everything else. it was only 5 years ago that we couldn't get people to pay attention to us. So that goes to show the example that Paul was mentioning about the speed of innovation, the possibilities that things kind of bump along, and then all of a sudden, everyone knew it was going to happen all the time. So that's a bit of I think of a near-term example that many people here around this room and in academia and labs had a part to deal with. Well, to talk about quantum, a little bit of the history of quantum. It was in 2017 that a number of PIs from UChicago and Oregon and elsewhere were working on what was called the National Photonics Initiative, about trying to push effectively quantum technologies. And luckily, I had the chance to meet with him and many others. And we, as a new administration and President's leadership, decided that we were going to embrace this. And we led to a quintupling with the support of Congress on quantum technologies. The President took the leadership on the National Quantum Initiative, signed that with Deputy Director Kratsios, CTO Kratsios at the time, and led to the explosion and the big ramp associated with that investment. Once again, not that long ago. Obviously, there were efforts by NSF, by Commerce that now I'm lucky to be a part of, and DOE. I'm around layers of that. There was NSF efforts that came out that went into Santa Barbara, went into UChicago on biology, various NIST efforts around manufacturing, a lot in networking that were done in Colorado, and the 5 quantum centers that happened with DOE. 2 were in the Chicago area, associated with a number of the universities. The most entertaining phone call I got after that was from a well-known person in the Chicago community after that announcement that said, "Hey, thanks for the 2 of them ending up in Chicago. Why didn't we get all 5?" So I'll let Paul guess who that phone call was from. He'll get it in one guess, I'm guessing. Obviously, we built a lot. The first phase of the National Quantum Initiative that the President directed us to go do, President's leadership on that, was to a large degree focused on discovery and innovation, right? Laying the foundation, scaling, so to speak, the discovery aspects of what we were doing. I think that went very well. There's many different aspects. You go around to universities that we funded, you go around to the labs that we funded, and the centers that NIST and DOE and others, NSF funded, I think went very well. But the intent always was what's next. We were looking at what to do after the initial 5-year period. And so we're there now. I wish it would have happened a few years ago. 5 years ago was done earlier. This is where leadership in politics kind of comes to play about what do people go focus on. The President sent a letter to now Director Kratsios, rather than Deputy Director Kratsios at OSTP, and highlighted AI, semiconductors, and quantum. So we're off executing on the President's plan. So leadership matters, I think, as many of you, especially in academia who deal with lots of young people, right? Leadership is the mixture between being both idealistic and tough-minded to get things done. And hopefully with a little bit of wisdom, you still maintain a little bit of the idealism, but also know how to get things done. And that's what we're trying to do. We're trying to look at, for the quantum sector, what's the hill? What's the set of grand challenges? And I think many people in this room know what the grand challenges are. And those grand challenges are being worked on by the same general group of people, maybe in slightly different seats, at OSTP, at Commerce, at DOE, at NSF. We've done it before. We mapped it out before, and we're looking towards the future. So the future is not defunding discovery. That will continue. But how do we look for devices? How do we have specific grand challenges around quantum computing? And we're going to do that. Around networks, around sensing and applications like medical topics. On manufacturing, I think one of the things that we've all learned in our challenges with China is they're very good at scaling and manufacturing. They're extremely good at that. we're going to invest also in the quantum realm around foundries, around tools, around technologies, and the assets that we have, the American taxpayer support, to take a look at focusing on also on that. So there's a series of those things that we're doing. I can speak obviously most directly to the Commerce Department. Secretary Lutnick is extremely focused on the same three topics. Just to highlight the ones that are most visible, what we're doing on semiconductor fabs is scaling massively, right? So the TSMC fabs, just to pick on one of Micron or TI that are getting announced and built, they went from $65 billion in one fab to $165 billion in three fabs in Arizona. I think there's a lot more to come on that kind of aspect. Obviously, I talked about AI and the AI rollout this week, but the Secretary is extremely focused on executing on the quantum side. So have direction from the President, have direction from the Secretary, and I think I can say the same thing for DOE and NSF getting directed from the White House. So as we take a look at where we're going, as I mentioned, I think a lot of the sensing aspects and direct applications that can be had, whether it's for medical, whether it's actually for semiconductor fab and metrology and measurement, as we move from 7 to 2 to 1 nanometer of where we're going, and the metrology and the measurement that we're going to be able to head down the road on that, I think quantum and quantum sensing is going to be very valuable. On the networking aspect, obviously there's lots of work that's been done at Commerce and NIST and Boulder and so on. There's an interagency effort that was done a while back that hasn't moved forward. I think we'll be looking at it called DCQNet. And so those are things that I think that NIST and others who have been a part of will take a look at. There's a lot of efforts at DOE supported national labs on that. Who knows? Maybe we'll even go to space. We'll see. And obviously, the most obvious ones, which is of quantum computing. This is the right time. This is the right place. There are people here in this room who have been very much associated with this. This is the time to push it over the edge. It's close enough. It's a little bit like when NVIDIA came to DOE and said, please use the GPU. And we said, And then after a long period of conversations, we said, we'll give it a try. And that, I think, was a major trigger of what we're seeing here today. And so I think that's exactly where we're at. What you saw in this week around AI and what's coming out of the White House, I think it might end up, I think we're thinking about what that looks like for quantum. It could look very similar to the sort of things that you're seeing, the specificity. So once again, you saw an AI action plan. You saw things like AI infrastructure build out. You saw exports. Now, quantum is a little bit different, but I think if you step through that, I think we're very much thinking about the specifics of a strategy. I think we're thinking very specifics about an execution plan and grand challenges with specifics, not generalities, of what we're going to go try to fund and what we're going to go try to build. And we'll also be engaging with Congress on the reauthorization of the National Quantum Initiative. I testified on that when I was a civilian in the last time. It hasn't been passed. We're going to try to encourage Congress to pass it, and we're going to try to encourage working with staff and members to get edits in that align with that with the specifics. So I think we're very excited about where we're going. That's a little bit of a teaser. And I will now move from one Naval Academy graduate to yet another Naval Academy graduate as you get to hear from someone leading with a number of the universities here represented today.
Thank you. Thank you. Paul, thank you so much. I really appreciate that. Great. Hello, Todd Young, represent the state of Indiana, and I welcome all of you. So grateful to Secretary Lutnick and the entire Department of Commerce. Good to hear from Paul. One of the things that Paul mentioned was the importance of Congress acting in this realm. There are already a number of authorities that Commerce is operating under. They're doing a great job laying out a plan and working the plan, but Congress needs to reauthorize the National Quantum Initiative. I'll be working with Senator Cantwell on that effort. This is a great week. Just to step back a little bit, I heard Paul mention the AI action plan, laying out the administration's strategic vision, their agenda as it relates to artificial intelligence, but just the thought leaders and experts that we see involved today and this event focusing on quantum, you sort of mix all that together, and I think it's a really exciting time in the world of tech policy. As it relates to quantum, we have quantum computing, communications, the ability to revolutionize drug discovery, our cryptography implications of continued quantum development, material science. There is a lot of interest here on Capitol Hill in quantum technologies. And so for those who wonder whether or not Congress is going to act, because the administration has been a flurry of activity over these last 6 months, this is an area that I anticipate bipartisan congressional action in. And we have this uncanny ability when we're in competitions as a country, historically and in recent history, of acting, using those challenges by adversaries oftentimes as focal points for congressional action, even when, let's face it, we're a fairly polarized country from a political standpoint. So we will act. That's one message I'm hoping you take from this. And we think it's very important to reauthorize the National Quantum Initiative. And we do, in part because it helps provide and reauthorize the right formula. The only way we're going to stay in the lead as it relates to quantum advancement is by partnering from across industry and university and the government to establish thoughtful partnerships, draw from the different talent and expertise we have in those institutions, and then inform our policymakers what is needed to keep advancing this technology. We have a model for this. I say that with a certain measure of pride of authorship. The CHIPS and Science Act was another tech area in recent history that we came together on because we heard from the stakeholders, from people like those in this room, how important it was for us to act. So ultimately, we'll get to the point where we're in the process of standards development. Standards will be developed by other countries if the United States doesn't lead. President Trump, his Commerce Department, and others throughout government, certainly throughout Congress, recognize the importance of the United States of America establishing the standards of this quantum age. We are also prepared to make strategic investments. I was encouraged, but not surprised, to hear from Paul that there will still be investments made in technology and research and all the rest, and it sounds as though the administration intends to make this one of the priority areas for their future investment. I'll be pushing them and encouraging them in that regard because our very economy, our national defense, our way of life depends on quantum advancement and the United States leading the way. So thank you again for letting me say a few words. It's time you hear from others, and to the extent there are people out here that I can partner with to enable our quantum economy and quantum development to move forward, I am all in. Well, God bless.
Thank you so much, Senator Young, and thank you, Deputy Secretary Dabbar, for sharing your perspective, your understanding, and your strong leadership in quantum, specifically actions that will be taken and the vision of where the U.S. can go next. Now I'm delighted to introduce Dr. Mark Saffman to give us a short primer on what quantum actually is and what it enables. Mark is professor of physics and director of the Wisconsin Quantum Institute at the University of Wisconsin-Madison, as well as chief scientist at Inflection, which works to commercialize atom-based quantum products. He is one of the leading voices in quantum information science. Please, Mark.
Thank you, Nadya, and thank you for taking the time to join us today for this discussion of quantum science and technology and its importance for the United States. Now, I can't boil a whole semester down into 5 minutes, but I'd like to start by briefly explaining what quantum technologies are. The topic can be mysterious to non-scientists, and even for experts, it can be hard to grasp all the consequences of quantum science. Quantum technologies are based on quantum mechanics, which is our fundamental theory for understanding nature at a microscopic scale. The properties of elementary particles, atoms, molecules are all described by quantum mechanics, which predicts unusual phenomena such as superposition and entanglement. I'll say more about what those phenomena are in a minute, but for now, let me just say that the properties and behavior of quantum particles are very different than what we experience in our daily lives. We can put many atoms and molecules together to create materials, electronic circuits, chemicals, medicines, etc., etc. However, when we have many quantum particles together in larger systems, the strange quantum properties don't normally rise to the surface and are, if you like, hidden, even though quantum theory is still the basis for understanding how things work. That understanding had its birth in 1925 with the invention of quantum mechanics, and since then, there have been a host of scientific and technological developments that have relied on the quantum theory. Let me give you a few examples. In 1947, the first transistor was demonstrated at Bell Labs, which then led to the integrated circuit, the semiconductor industry, powerful computers that fit in the palm of your hand, and the electronic processors behind the AI revolution, which we just heard about, and created enormous wealth. All of this started with the understanding and perfecting how transistors work, which is rooted in quantum mechanics. In 1950, the first atomic clock was invented at Harvard University. The invention now forms the basis of the global positioning system, which enables us to navigate globally using only our cell phones. In 1960, the first laser was demonstrated at Hughes Research Labs. Laser technology now has a myriad of applications, including as an essential ingredient for high-speed optical data transmission over the global internet. And in the early 1970s, magnetic resonance imaging, or MRI, was invented at Stony Brook University. It has become a standard and preferred method for non-invasive medical diagnostics and provides health benefits to millions of people every year. Again, the technology relies on the quantum mechanical behavior of atoms. These inventions, the transistor, the atomic clock, the laser, MRI, all became technologies that have provided societal benefits and economic prosperity. There are many more examples. Collectively, these developments from the first 50 years or so of quantum mechanics could be called quantum 1.0. We are now in a new era, quantum 2.0, where we are making use of quantum phenomena in new ways. It turns out that these quantum properties, superposition and entanglement, are a kind of super force. By using quantum aspects, we can build more powerful supercomputers. We can transmit information securely over long-distance networks. We can deploy more powerful and precise sensors and do things like navigate precisely without GPS. The truth is, if you're not using quantum 2.0, you're going to be at a disadvantage compared to any adversary who does. So what are these quantum properties? Let me start with superposition and give you an example from computers. In all conventional computers, data is stored in zeros or ones, binary bits. Think of a light switch that is on, a 1, or off, a 0. Those are the only possibilities. Quantum bits, or qubits, can be 0 or 1, or any combination of both at the same time. That is superposition, having both values at once. It sounds a little crazy, or maybe a lot crazy, but it allows quantum bits to store massively more data than conventional bits. Quantum computers built with qubits have recently demonstrated that they can perform certain calculations millions of times faster than any conceivable conventional computer. That calculation was not quite yet something useful, but we are on the verge of being able to solve real-world problems. For example, designing new materials with enhanced properties on quantum computers, which will have enormous impact for our economy and national security. The second quantum aspect I want to highlight is entanglement. This is even more mysterious than superposition, and it refers to what can happen when we make quantum particles interact in a very controlled way. Entangled particles act like a single superparticle with magnified properties. Using entangled superparticles, we are developing better clocks for timekeeping, better sensors for motion and gravity, and for sensing electromagnetic fields. These quantum sensors will provide revolutionary capabilities for autonomous navigation, for studying properties of materials and biological systems, medical imaging, and for detecting adversaries. To conclude, I'll note that quantum mechanics was invented in 1925. Today, in 2025, exactly 100 years later, we celebrate IYQ, the International Year of Quantum. We have a panel of industry leaders with us today who will discuss where we are and where we are heading on the path to developing transformative quantum 2 technologies. The precise timeline for useful and widely available quantum 2 devices does remain fluid. Nevertheless, I want to emphasize the importance of continuing to invest in the underlying quantum science and supporting the collaboration between universities, government labs, and industry that has been so successful in creating quantum 1.0 technologies and will continue to be essential as we look towards the success of quantum 2.0. Thank you.
Thank you so much, Mark, for explaining our Quantum 2.0 revolution in technology moving forward. We're now going to transition directly to our panel discussion. I invite the panelists to come up now. You're going to hear directly from leaders in quantum industry who are shaping the future of computing, networking, sensing, and more. This panel is going to focus on funding, workforce development, national security, and American competitiveness. And there is going to be time for questions at the end, even if you want to ask just about entanglement and superposition. Please feel free. So joining us will be, here we are in order, Jay Lowell, who's the Chief Engineer and Senior Technical Fellow of Boeing's Disruptive Computing, Network, and Sensing. Pranav Gokhale, Vice President and General Manager of Computing at Inflection. Hannah Parnes, Head of Policy at IRO-Q Quantum Hardware. Jay Gambetta, Vice President of IBM's Quantum Initiative, and Alan Ho, CEO and co-founder of CoLab. And moderating the discussion was Kate Timmerman, CEO of the Chicago Quantum Exchange. Please welcome our panelists and our moderator.
Thank you very much, Nadya. It's a pleasure to be here with you, hearing about all the work that's being done in quantum nationally as well as in the Midwest. And honestly, I'm very honored to be on the stage with these really impressive industry representatives to talk about, one, the work that they're doing, the importance for the nation, and honestly, the importance of collaborating. I think everyone here are people and representing organizations that really collaborate with lots of us in the region as well as nationally as well. So I think I'd love to start by kind of going down the line and letting everyone introduce themselves and maybe talk about kind of, how you feel your companies are most investing and the importance of quantum for you. And I know that's a big question. Jay.
Hi, I'm Jay Lowell. I'm a Principal Senior Technical Fellow at the Boeing Company, and I lead all of our company's quantum technology research and development. Our company has a pretty diverse portfolio looking into many different quantum technologies and how they will benefit our customers and help us develop new products and services. I think the two things I'd probably highlight as our most ambitious activities are the development of quantum-based inertial navigation capabilities and having done the world's first flight test of those sensors, we feel like we have done a good job keeping the U.S. in the lead in that technology. And also our commitment to develop space-based quantum networks, which we are launching the U.S.'s first quantum satellite in next year, which will demonstrate a protocol that's needed for all quantum networks on that satellite.
Thank you, Jay. Pranav?
I'm Pranav Gokhale from Inflection. I lead our quantum computing efforts. You heard from Mark Saffman as well, who's our chief scientist of quantum hardware. Our company develops both software and hardware for quantum. On the hardware side, we build both quantum sensors and quantum hardware. And the quick reflection I'd add to your question is we think that the national security and national resilience applications of quantum are very compelling. Things like GPS denied navigation with inertial sensors, better clocks, and quantum computers for building better materials for both civilian and military applications.
Thanks, Anna.
Hi, I'm Hannah Parnes. I'm with AeroQ Quantum Hardware, and I actually was a Senate staffer myself, so hopefully I can speak your language. We are a quantum computing hardware company that is laser focused on one thing, developing quantum computing chips that will eventually become a full-scale quantum computer. And what's interesting about our approach is we are the only commercial effort pursuing our specific type of chip hardware. There are a few academic labs, including 3 in China, that have popped up mysteriously after we began publishing. So there is going to be intense competition, but we are very much a next generation approach to quantum computing, and we're proud to be based in America and hope to continue to grow here.
Thanks, Anna. Jay, go for it.
So I lead IBM's effort for quantum computing. We've actually been working on quantum probably as far back as the 70s in trying to understand what quantum information science is. But our goal is very simple, to bring useful quantum computers to the world and do the algorithm research to make sure that whilst we do it, we understand how it will apply in different domains, including security and working on algorithms that quantum computers can't break. Since 2016, we made our quantum computers available to the world, and we've grown an ecosystem with over 300 different partners, over 3 trillion executions, and many different universities that we're partnering with to work to create this ecosystem, really train the future, and make an industry, and that's the goal of IBM.
And last but not least, Alan.
Hi, my name's Alan Ho. At CoLab, our mission is to bring the capabilities of the semiconductor industry to accelerate the building and manufacturing of quantum computers in America. So what makes CoLab was started with Dr. John Martinez, who's most well known for leading the Google team to this one of the America's big technological advances, quantum supremacy. And what we saw is that there's an opportunity, especially as America is trying to onshore semiconductor manufacturing in the United States, that if we can take all these capabilities the semiconductor industry is doing and then apply it to building quantum computers, not only will we be the first to build a quantum computer, but we'll be the first to manufacture quantum computers at scale in America, and we'll be able to export that to the entire world. So that's our big mission, is to build a supply chain and build quality jobs in manufacturing in the United States.
Thanks, Alan. I have one kind of follow-up question. On the manufacturing piece, there's manufacturing, quantum technology developers doing manufacturing, and then there's also, the component suppliers and subsystem suppliers that go into your systems. Where do you think the U.S. stands in terms of that, and what could we do better in that as well?
So I think actually one of the one of the things I want to dispel is that actually U.S. is #1 in manufacturing quantum technologies. And as you know, it's a lot easier to be #1 than it is to offshore all your manufacturing trying to bring it back, right? So a lot of the technologies that we use for quantum technologies is actually the same technologies we use in fabrication. And maybe Jay can also talk a little bit more about how they're leveraging.
Yeah, I agree with Alan, and everyone should know that the U.S. is definitely leading in building. All our quantum computers are built solely in the U.S. We have over 13 available now to clients that are all in Poughkeepsie, New York, and we've actually managed to distribute quantum computers to South Korea, Canada, 2 in Japan, about working towards India installing one in Spain. So right now, I agree with Alan. We're at a point where we're manufacturing, and I agree that it's about keeping the speed and progress and investing to keep us in the lead.
And if I could quickly add, so we also produce our chips using commercial semiconductor foundries, and we work with one that's based here in the United States. However, there's an opportunity for more R&D focused foundries that have more flexibility to do smaller prototyping runs, and I think that will be essential for the continued development of what Professor Saffman called Quantum 2.0. There are other countries that are taking the lead, in my opinion, on these more R&D focused foundries. So the United States should offer the same infrastructure here if we want to avoid the situation we saw when there was a chip shortage and we had offshored a lot of the manufacturing capabilities for critical technology.
Let me, one thing where we're not necessarily in the lead is that not all quantum technologies are based on semiconductor electronics manufacturing. There are some of the quantum computer technologies really are built on lasers and optics, and much of that laser manufacturing, in fact, almost all of that laser manufacturing is done in Southeast Asia. Almost none of it is done in the US. The US does have assembly technology to do assembly and packaging of some of these lasers, but there are, as you look across the breadth of quantum technologies, there are places where the U.S. is securely in the lead, and I think that the other panelists have identified that. But there are portions of the technology supply chain that are relevant for these other areas of quantum technology where the U.S. is really absent in that supply chain picture. Another area that's similar to that is actually the fabrication of large cryogenic systems, where Europe has had a long-standing lead globally.
Thanks, Jay. I'd love a follow-up question. Kind of what are the long-term ramifications of these different pieces if the U.S. does not lead? I know it's a big question.
So I think that
forecasting into the future.
Yeah, thanks.
Yeah.
So I think what this means is that we're going to be forced to accept constraints in the way that we engineer, design, develop, or produce products. And those restrictions are essentially going to either going to hold back the pace with which we can develop, or are going to place performance and cost and performance and cost limitations on the kinds of products that we will be able to develop. Those not having the ability to have some insight and some ability to produce things all the way up and down the supply chain really does provide pretty substantial constraints on what you're able to do and how you're able to design new things, because you really are limited to only the things that you have available to you. You don't have the ability to create those custom things that you might need that aren't in the market today.
Thanks, Jay, for dealing with a very hard question. Hannah, because you do have this policy expertise, I'd love kind of your thoughts about what are the levers of government that might be able to be pulled to enable us to move forward.
Sure. So the United States has taken some really significant first steps towards fostering quantum R&D and commercialization in the United States. However, a lot more needs to be done. So first of all, with the National Quantum Initiative Act in 2018, that was a fantastic first step. However, it's overdue for reauthorization. We should not give up our lead there, and that should be reauthorized as soon as possible. And also, a lot of programs that were either authorized in the NQI Act or the CHIPS and Science Act have not been fully appropriated. So I think fully funding these programs that many of your bosses wrote and passed is very important to follow through. And on the same page, some programs that have been appropriated haven't been fully implemented in the relevant agencies. So there's opportunities for oversight and through notice and comment rulemaking and other ways to engage with stakeholders, ensure that these programs are fully implemented. And then looking forward, there's a lot of opportunity to continue to invest in quantum technologies. The United States is starting to fall behind on public investments in quantum technologies. China has invested, I think, $15 billion by now in public investments. The United States is estimated around $6 billion, and my reading of the numbers is that that's authorized, not appropriated funding. We're in a really unique window of opportunity while the technologies are still being developed, are not yet fully mature, are not yet fully deployed, where we can cement our leadership position in this race. And if we don't continue to take step forwards, we will lose our position, and that can have catastrophic consequences for economic competitiveness, national security, global hegemony. There's really significant risks if we don't continue on this path and take bigger leaps forward.
Thanks, Anna. You know, we've talked a lot about kind of technology development thus far. I think a very crucial piece of this is workforce development as well. And, you know, Jay Gambetta, you mentioned that you guys have been doing quantum research and moving that to manufacturing for, you know, decades now. Would love to hear, I think, I'm pretty sure on this panel, you guys you have the largest quantum workforce on this, on the panel. I'd love to hear your thoughts about kind of what are the programs and initiatives needed and at what scale to really build the quantum workforce, and particularly to meet, you know, the next 10, 20 years?
Yes, so obviously we do employ a lot of people, but in something that is emerging and it's a race and it's an ambitious area, this is something that inspires people. It inspires students. It inspires people to want to get into this field. And so I think when I think of workforce, I think we have to keep that inspired, that race. We're in a race. We're doing well. Yes, let's keep everything going, but the students are essential for that. And when you look at this technology, it's not just physicists. Yes, we need more physicists. It's going to be developers. We need developers. We need computer scientists. One of the biggest challenges we have as we go forward is the applications of quantum computing are all proven in like pen and paper. You look at AI, most of the applications are heuristic. And we're seeing how much heuristic algorithms matter. So we need to get the mathematicians, the computer scientists, all of these coming in. And so when I look across this, you're going to have engineers, you're going to have physicists, developers, chemists, health and life, like we're partnering with Cleveland Clinic on quantum computing applications to health and life science. And you're going to have examples there. So when I look at it, we need more initiatives. I would ask making sure that we continue investing in the hardware, the device physics, better devices, also investing in the algorithms, and also bringing computer science to the table for a field that has actually been in the past very much dominated in the physics. And then, of course, I know all the wonderful things that you've done at Chicago Quantum Exchange in bringing these ecosystems together.
Thanks, Jay. Jay, the other Jay?
Yeah, I think having the diverse portfolio that we have, we see a lot of the similarities to what Jay discussed, but I think we view it as that the physicists are really the tip of a very, very large and very broad iceberg. As you develop these quantum products, you have to have people who understand all of the different engineering disciplines that go into the components, people who understand how to put those things together, so you need manufacturing expertise, and in many cases, you need specialty manufacturing expertise. I was having a discussion at the event yesterday with people who work on building large-scale cryogenic systems, and they pointed out that one of their biggest shortages is people who know how to weld process piping that can transport cryogenic fluids from one place to another. This is this is not a skill that takes a PhD, but this is something that takes years to develop the skills to do this as a welder, because it's not like welding copper pipes in your home. It requires extreme precision because you're having pipes that have to handle hundreds of degrees of temperature difference between the outside and the inside. And so there are very specific ways to do this, and it takes a long time to train them. So there are many other examples like this where there are things that we see as technologically sophisticated where we have to have training, but there are many others that are, at first glance, seem ordinary, but they still require specialty training and expertise that extends all the way down to people who could be coming straight out of high school or a trade school.
Yeah, I'd really quickly for the audience, kind of when we think about the quantum workforce today, it's very small in the Midwest, but it's going to grow significantly over the next decade. We have an NSF Engines Development Award that really forecast out that over the next 10 years, our three-state region will have between 80 and 190,000 quantum jobs, the vast majority not requiring an advanced degree. And I think I'd love to hear from you, Pranav, about how you're thinking about this, particularly as you're growing, honestly, in multiple places across the U.S.
Certainly, and I can follow up and second Jay's comments with just two personal anecdotes. At Inflection, two of our celebrated employees, one of whom is a vacuum glass cell technician. Her background was as a cake decorator, and it turns out that there's immense overlap between the skills that you need for cake decoration and for being a vacuum cell technician. Another example is our employee Victory from the great state of Iowa is one of our most senior quantum software engineers. He has no formal training in quantum computing. He was working Home Depot loading dock, but at the nights was going on github.com and contributing to open source quantum programming languages and became one of the world's leaders in quantum software development. So I think there's a lot of really impressive pathways, and I very much agree that the technician trade school pathways should be furthered for quantum skill development. Going back to the bigger question and bigger picture, one thing I'd point out is, so Inflection has become the largest private employer of quantum talent between our presence in Chicago as well as Madison. Just yesterday, we announced that we're moving our headquarters of quantum computing to Chicago. And this has emerged because of a very strong collaboration between industry, academia, and the national labs. My personal backstory here is an example, I think, where I came out of the University of Chicago. The default path may have been to perhaps go to one of the coasts to do quantum or start something. But I saw that there's this immense workforce coming out of the universities in Chicago and our region. So I spun a startup out with the support of the Chicago Quantum Exchange and the Duality Incubator. We embedded at Argonne National Lab to start the startup there and get the research off the ground. And in 2022, we were required by Inflection because we met Mark Saffman, who's leading the quantum hardware efforts in Madison. So these things come together in sometimes surprising and funny ways, but the common piece is that when you get together the end customers, the companies developing the technology, government funders, universities, and the national labs that Paul Dabbar spoke about, there's this immense force multiplier where every dollar that comes in leads to tens of dollars, if not hundreds of dollars, of economic value and local job creation. And that's not just Inflection, that's true for all the companies in this panel. We've all become members of the Chicago Quantum Exchange, which has become one of these regional connectors that make sure that the end customer demands get reflected in the technology that's being developed, whether at the companies, universities, or labs.
Thanks, Pranav. And yeah, anyone who else wants to jump in, definitely do so. Alan?
I just also want to chime in that for CoLab, we also are headquartered in Madison, Wisconsin. And so it's also an opportunity, right? Like we see all the jobs are being made on the coast. It doesn't have to be that way, right? We could spread this around the entire country. And we did it in Madison because of a lot of the support from the university as well as the state, right? And so I think there's a real good opportunity that as we bring more and more manufacturing back to America, that quantum can become a great source of jobs throughout the entire country.
Thanks. I think I'd also love to hear from whomever, Pranav, anyone, about the collaborations with academia and industry on the research side, right? That early stage R&D would love anyone's thoughts about that.
I'd be happy to give an example of a program called Welcome Leap Quantum for Bio. One of the amazing things that quantum can unlock is better sensing and better processing of large biological data sets. So think, for instance, of cancer data sets where you want to make predictions of which mutation or which intervention is going to be best downstream for human health. That's the kind of problem where it can become very combinatorially expensive. That just means hard to solve with even the world's biggest computers. we've been partnered with University of Chicago, this Welcome Leap Foundation, MIT, and a number of hardware platforms, including the great hardware that IBM has put out, to get the first ever instances of this problem running on real hardware. And it's the kind of thing where we know the limits of what the quantum folks know. We don't know anything oftentimes about human health, but we work with the Biological Sciences Division and the Pritzker School of Molecular Engineering at UChicago, who knows all of that. And maybe on their side, they don't know so much about qubits, but know that they might be able to solve some interesting problems. And that's where university partnerships, just one example, can be really effective in combining disciplines that otherwise wouldn't really talk so much, and especially getting them to the level of a commercializer in industry. Oftentimes, universities are very good at getting technologies to the point where industry can come in, but it does take industry to take that towards a product.
Maybe I can add. So I've always looked at the combination of universities, industry, and the national labs as essential. I'll give 3 examples. We have set our goal to build a fault-tolerant quantum computer. This is a computer that basically deals with the effect of errors by the end of this decade. Sorry, I apologize. Build a fault-tolerant quantum computer by the end of this decade. The universities are where a lot of the innovation in the error-correcting codes happen. They have novel ideas, and they invented this new way of doing error correction called LDPC codes. We were able then to adapt it to our hardware and basically have a legitimate, for the first time, plan that a fault-tolerant quantum computer can happen. So you go from the theorist inventing a new way of doing codes to working out can apply to the systems. Then you can go another step further. For us to build a large-scale fault-tolerant quantum computer, it has to be modular. The first to demonstrate the ability to couple 2 superconducting chips was actually done by a lab in Chicago. That same technology we've then adapted and developed and brought into our process to give us how we're going to build forward to be able to connect our processes together. And then lastly, on the algorithm side, the first, some of our partners, and this one of our partners, as I said before, is in Japan at a national lab there. They worked on an algorithm where they used 1/4 of Fugaku mixed, which is one of the supercomputers, and we're working on it now with the DOE and Frontier, so I expect to see that come out soon. 1/4 of the Fugaku combined with the quantum computer to look at problems and get comparable results to the best classical methods, and start to look at chemistry at a way that is actually getting comparable. So we're going to see it. And then from there, Cleveland Clinic, who want to take those chemistry ideas and ask, how can I look at drug molecules and things like that, have now adapted that technique and done a series of papers. And so you often see this flow from high risk, high reward. National labs are great at putting large-scale things together, and industries where our power is being able to iterate, to engineer, and to bring that. And to me, I think this tripod is essential for us to continue to lead.
Yeah, I can add another example to that. Or were you going to say something, Alan? Go on. One of the in building the Q4S satellite, which we're going to launch next year, demonstrating this quantum communication protocol, we've had engagements with the University of Illinois, Urbana-Champaign, as well as work at one of our subsidiaries, HRL Laboratories, which was previously mentioned as the birthplace of the laser. We have been working with researchers in both locations, and in so doing, they've helped us make sure we understand kind of the trade-offs that we have in building this kind of system. And as an industrial, what we bring to the table is the ability to do what they see as a lab tabletop experiment and do all of the added engineering that it takes to put that, instead of in an environment where the lab changes its temperature. So to do this communication protocol, you have to keep lengths stabilized to very, very minute degrees or minute distances, fractions of a micron. And in order to do that, as the temperature changes, everything swells and expands, and so all of this changes. So doing an experiment in a lab where the temperature changes maybe a degree over a day, not so bad. Our satellite, the temperature is going to change 40 degrees every 90 minutes. And so we have to do a lot of different engineering techniques that we build on top of these academic demonstrations to take them into an environment that is not the same as where many of these things are invented. And with things like sensors and communication networks, more so than with the computing domain, changing that environment and understanding how to engineer systems to work in that environment is one of those things industry does very, very well and can really amplify those early inventions and those early developments of techniques from the academic world and from even the government laboratories and turn them into real capabilities that can be fielded.
Thanks so much. You know, I'm hearing patterns of like direction being really important. The Wellcome Leap Trust, funding is very directed towards bio. I suspect that having Boeing being the industry driver really helps that move forward. You know, are there things that can be done at the federal level to really help with those directed investments? I think I leave this open to anyone. Go for it.
You can go.
Yeah, I'll go first. I mean, the question is, what is our competitive advantage for quantum as a nation? And it's like we're not spending as much money as China. Okay, I mean that was clear, right? We're struggling to create more STEM students, and right. So what is it? It's really public-private partnership, right? So if there's anything we can do at a federal level, it's to support more public-private partnership. But that's very tricky, right? Because any single time you talk about funding public-private partnership, people are thinking, oh, the money is just going to be becoming a handout to the commercial companies. I think the thing that I would have to say, especially for the folks in the room who are making these decisions, is that you have to do the hard work to understand what the private industry is doing with public and vice versa, right? And fund those initiatives.
Yeah, and I'd like to just add to that there's an opportunity to think about the entire innovation life cycle, which starts at the foundational basic research and then continues on to development, to commercialization, to scale manufacturing. And focusing only on one part of that life cycle will not get us to quantum leadership. Another example of how public-private partnerships have impacted industry growth. As I said before, we're sort of unique in our chip architecture. We actually will be able to put an entire full-scale quantum computer on one chip. It's different than other approaches. But that also meant that we needed to de-risk the technology and demonstrate the foundational technology first before we raised a whole bunch of private capital. And we did that in an academic lab with sponsored research at another Midwestern institution, Michigan State University, where we were proud to be, but happy to be in Chicago now. And without the ability to demonstrate some of the foundational technology, we wouldn't be able to have spun out and become a commercial entity. So it's just so essential that the entire innovation life cycle is supported by the federal government, because without it, we will not be able to develop and commercialize these technologies.
I'll just add a note of appreciation to you all, because I think a key part of building this future is for policymakers and their staffers to become familiar with the nuts and bolts of quantum. I think that's a key ingredient to demystifying this, figuring out what's real, what the timelines are. So thank you.
Great. Thanks so much. I do want to say we're about to open up for questions, so prepare if you have any big important questions to ask this great panel. I think kind of to continue with that, are there, when you're thinking about quantum, it's a relatively broad field. We have many different kind of thrusts and sub initiatives within it. Are there specific areas where federal investment, and particularly sustained federal investment, might be most useful to you broadly, to your company, that you see just in general? Alan?
Yeah, I think one of the things that Paul Dabbar said is that there are three major investment. There's semiconductors, there's AI, and there's quantum. And I think it's really important to understand that those are not mutually exclusive, all right? So today, the highest value, AKA the most profitable thing to manufacture in the semiconductor industry is GPUs. It will be QPUs in the future. So when somebody brings to your table, hey, we want to fund this big semiconductor manufacturing initiative, I just would like you to say, okay, what about quantum? Is this initiative that we're going to fund going to be upwards compatible with quantum? Same with AI. Today, right now, AI is being powered by GPUs, right? In the future, AI is going to be powered by QPUs, right? So then when you got a bunch of people saying, hey, we need a bunch of money for AI, ask, well, is there going to be a portion of it cut out for doing quantum AI research, right? And so that's why I want to kind of emphasize that all three are not kind of mutually exclusive. And the last thing I just want to bring home is this idea of bringing the supply chain to the United States, as well as not just United States, but also our global partners, right? We have the opportunity to become the biggest exporter. We have the opportunity to take leadership in the world in building a global supply chain, right? And when you do that and you bring it home, there's a lot of great things that can happen, right? Great jobs, but also if you have the entire ecosystem within the country, the time it takes to take an innovation from the lab, like in a university or a national lab, out into production and in the hands of consumers who's going to create more economic prosperity for the nation, that's also drastically accelerated. So those are kind of things I think we should be thinking about from a federal level at this point.
Great. Jay, I think you have a...
Yeah, so I think the time is now to be ambitious. We heard from Paul Dabbar. We're at a point where this technology is going to be, in the next 4 years, it's going to do amazing things. We need to set ambitious goals, and we need to set them to the level that it will realize outcomes. If we can get those outcomes of ambitious goals, many of the pieces will fall into place because everyone has a part to play to achieve something that is ambitious. So what I would leave with you is, yes, the NQI and things like that, we've got to get that through for the foundational, but my view is it's time now to be ambitious in this field and set our sights so that the US is the first to have a fault-tolerant quantum computer, and more importantly, the first to use it for advancing some scientific application.
I'm loving like the diversity of opinions here. So I really want to hear everyone. So everyone else be prepared. I'd love to hear from you.
Okay, fantastic. I think that building on what my co-panelists have said, but we need to be supporting innovation, not only supporting the technologies, the quantum technologies that are leading today, but thinking about the ones that will be the most competitive 5-10 years in the future so that we can sustain our leadership and continue to be competitive for the years to come. And I think that requires recognizing that a lot of innovation happens, in academic laboratories and national labs, but also in small and medium-sized businesses that are taking big risks for the technologies of tomorrow, the next generation quantum technologies. So that means for Congress to recognize that sometimes non-traditional contractors need to have pathways and opportunities to engage with programs or access funding so that the most innovative and groundbreaking technologies can be supported here in the United States. And one final sort of anecdote I want to add, because it might not be clear for some of the folks in the room, other countries are being incredibly aggressive in recruiting small and medium-sized businesses. They're offering tens of millions of dollars of cash, not tax credits, cash, to open labs, headquarters in those countries. So the United States has this fantastic ecosystem, but it needs to continue to build and support, especially the most innovative and smaller companies, so that we can continue to have a full industry here in the United States and not have to deal with offshored critical technologies.
Thanks, Anna.
I think back to what Paul Dabbar was saying about how there's this critical moment where DOE researchers were asked, hey, check out this GPU infrastructure. What could we do with it? And the rest is history of all of AI. And I wonder if that moment had not happened where these DOE researchers had been introduced GPU, we would be living in a very different world. And God forbid, maybe that had happened in China instead first. We'd be using DeepSeek instead of ChatGPT or whatever. And so I think we're at a similar moment right now in quantum where we should be asking ourselves, what serendipitous things could happen when we equip the leading researchers in the US with quantum computers, with quantum sensors. And I think it's incumbent upon us to make that happen and power the next generation of maybe the ChatGPT moment for quantum.
So I think there's an interesting role that everybody in this room plays in the development and the successful future of quantum technology in the United States. The people in Congress and the lawmakers have to ensure that the kinds of policies that we have are, as Hannah pointed out, they're supporting the entirety of the development life cycle from ideation through to the development and deployment of that technology in a commercial sense. There is a role in the people from the executive branch of the government to make sure that they are ensuring that the government has competence in the people who are in the executive branch and that they are working on setting strategy for those things that are important as public infrastructure or public capabilities that are needed that are not necessarily purely commercially driven, but rather quantum aspects of quantum technology that really benefit the greater good of all the U.S. GPS is a great example where the government, in its expertise of understanding how to address particular aspects of the problem, was able to create something that no commercial vendor would actually go out, but the government could take that long-term risk because they had people within their walls who had the expertise, who had the foresight and the long-term strategic planning to understand how this would make a better public good for the rest of the country to consume. And those of us on industry and in academia have a role to continue to drive, as Jay pointed out, to be aggressive and to try the big things that are substantive, that will show that we are continuing to make progress and will create this virtuous cycle of investment into those areas where we show great progress to further that progress ahead without having to be at the mercy of a government funding cycle, but rather driven essentially by the value creation of the technology itself. And I think if we all play our parts together, we have the opportunity to make this a great technology for our country and for the world and make the world a better place.
Thanks, Jay. Yeah, I'd love to open it up for questions. There's a mic runner. If anyone has questions, raise their hands. In the meantime, I'm just going to wax poetic about, I really liked how we heard multiple times that you need that essentially support and funding across all stages of the life cycle. That was very helpful. And, I could imagine some people wanting more funding in one area than another, but the fact that the whole quantum community is pretty much in lockstep about the need for that constant piece. Does anyone have any questions? Oh, Tyler, there's some. We have a mic runner. Todd, do you want to just begin since? Okay.
Hi, Jay.
There you go. Sorry.
Jay, I like what you had to say about we. I want to ask you, you've been around long enough to remember a sense of patriotism from previous decades. What do you think it's going to take to reinforce the we right now?
I think doing great things, as Jay points out, doing great things is inspiring. There is nothing that brings people together like coming together to do something that is truly hard and truly awe-inspiring. That sense of internal gratification and that becomes a collective sense of that gratification and brings people together towards that goal. That I think that's the kind of thing we will see, and we are seeing this in this field. It's an interesting point in time. I mean, I'm sure that others here on the panel would agree with me that we're in a situation where, as a commercial players, we have a very deep-seated sense of competition in the commercial marketplace. But within the quantum technology landscape, the sense is very collaborative. We all understand we're driving to this collective good. And we all need to be moving in the same direction. And as long as we're all moving in that direction, we're happy when our competitors make advances almost as much as we are when we make them ourselves.
So my last question is, how often do you see each other to reinforce that sense of combined effort?
I see these guys regularly.
I mean, I think an example is most of us saw each other yesterday in Chicago, right? So.
Thank you all for being here. My name is Jay. I'm a third year at the University of Chicago, and I'm just wondering, beyond the technology parts, once we have established easily to use quantum computers, what do you think the privacy implications look like once our current cryptographic methods can be easily defeated by quantum computers, and how should we prepare for that in advance?
So I can answer that. So the government has already taken a very, very good leading effort in standardizing what we call quantum safe algorithms. NIST has down selected already to these algorithms, and everyone has tried since 2016 in developing these algorithms to break them. And it turns out that very strong evidence that they cannot be broken by a quantum computer. So there is a solution. There are other solutions where you can bring some exotic things like QKD from quantum to even enhance that. The biggest problem in transitioning for the security is actually it's an enterprise problem, and it's an understanding of where security is used. So security was kind of developed before software was, let's say, modular in nature. And so when you're using security, it's embedded everywhere. And so the harder question is, how do we go to a future where we can be crypto agile so that if in the future quantum algorithms come that break those, or even more importantly, classical algorithms come to break them, updating security is as simple as a patch. That is a very hard enterprise and also government challenge of actually going to there. So the core theory is there, and it says these algorithms are safe. The implementation is going to require a lot of work, and my recommendation is both focus on the quantum safe algorithms and how we get the infrastructure in place to go there. IBM has taken a leaded effort already in our mainframe business has been quantum safe for a very long time. And there will be, as we go into the future, there are ideas that you can use quantum mechanics to provide extra security on top.
Yeah, and I want to quickly add that the quantum safe algorithms are only as useful as the information that they protect. So it's imperative that on both the government and private sector side, that there's a real inventory of what is the most sensitive data that should be protected by these algorithms. And I also want to echo something that Senator Young said, that we need to be thinking about standardization because we have somewhat of a blank slate in quantum technologies. And if we don't take a leadership position on standardization along with our international allies, China will set the standards, and that will have a dramatic impact on how the technologies are evaluated, on what's considered responsible use. So there's a lot of opportunities on standardization as well.
Yeah, and we're already seeing that in the post-quantum cryptography domain, where China's released its own encryption algorithms separate from those that the U.S. and the U.S. and Europe have agreed are a strong foundation for the world. So,
I just want to also add that it's not just post-quantum cryptography that we have to be careful about. It's actually Bitcoin as well. So as the world is relying more on Bitcoin, there are right now 6 million coins that are in wallets that are not protected by Bitcoin, protected by post-quantum cryptography algorithms. One of those wallets has $25 billion in today's value. And the estimated value in 2033 is going to be on the order of $7 to $10 trillion. Worse yet, stolen Bitcoin today is actually one of the #1 ways they fund terrorism and illicit crime around the world. And this is state-sponsored by North Korea, that they're the most known to steal Bitcoin and use it for illicit means, but for other adversaries of the United States. So we have to think, now, what does it mean with policy? Well, we need to figure out a way to recover those coins in a safe way that doesn't get the companies thrown in prison, right? And this is something that the U.S. Treasury can work on. This is something that Congress can work on. We'd already had great progress with the Genius Act that just came out just now. So that's another thing that we need to be thinking about very soon.
Quick second to Alan's point in the context of Crypto Week, and I'll add Ethereum also uses this ECDSA encryption scheme, which is vulnerable to the exponential quantum attack. So this is perhaps 5 years ago, it would have been the problem of just the fringe crypto people, but now it's so mainstream that I think it does need to be on the radar of the government more broadly.
Thanks so much, guys. I think we're going to wrap up, but after Brian closes out, we are going to have mingling opportunities. So at this point, I just really want to say thank you for joining us. Thank you to our amazing panelists for sharing your insights with us. Really appreciate it.
Yeah. And to echo Kate, thank you so much to our incredibly insightful discussion and our very knowledgeable panelists for this this increased understanding of where we are right now in quantum, what some of the challenges and opportunities are. So to close the program, I'm pleased to introduce Brian DeMarco. Brian is the Chief Technology Officer of the Illinois Quantum and Microelectronics Park, Director of the Illinois Quantum Information Science and Technology Center, and Director of the NSF Quantum Leap Challenge Institute for Hybrid Quantum Architectures and Networks, as well as Professor of Physics at the University of Illinois at Urbana-Champaign. Brian, please.
So first of all, thank you. Thank you to the University of Chicago for organizing. Thank you to Senator Durbin for hosting. Thanks to our incredible panelists and to all of you for attending. One of the benefits of being a university professor is you get to stay connected to the younger generations. And you get to see their excitement about quantum. You know, for example, I invited Hannah to come down to the University of Illinois for a fireside chat. Whenever you do that, you always get nervous how many people are going to show up. That was a 400-seat auditorium that was packed, and they were enthusiastic, and they mobbed Hannah at the end. They wanted to know all about it. Another benefit is you get to learn new things. So, for example, my graduate students explained to me what it means when somebody texts TY to me. I was like, TY, what does that mean? They explained it to me. They have also shown me that one way to do speeches like this is to read notes off of a phone, so wish me luck. This is something new for me. All right. So I want to come back to a few things we heard today from our various speakers. In the very beginning, we heard from President Alivisatos that one of our superpowers as a nation is creating innovation ecosystems. And you saw that at its best today, in my opinion. You saw a Midwestern innovation ecosystem involving academic researchers and industry, national labs, developers of technology like Colab, like IBM, like IRIQ, and users like Boeing. And you also saw what is essentially a marketplace that encourages competition. There are competing technologies you saw up here today from competing companies, but also when possible, the free exchange of ideas, which we also heard about from our panelists and how important that is. So let me close with some thoughts on programs and policy. And we heard this echoed over and over again today from people like Deputy Secretary Dabbar, from Senator Young. Now is the time to go big. There are programs that we didn't hear about today, which are very successful, like the DARPA Quantum Benchmarking Initiative, which Colab and IBM are in, which is a really aggressive program to get quantum computing as quickly as possible over the finish line to market value and societal impact. Let's think big about other new programs that develop the manufacturing base. We heard from Jay Lowell today about how we do not have a big manufacturing base of large-scale cryogenics, which are essential to scaling some quantum technologies in this country. The two big manufacturers are in Europe, in fact. We also heard from Hannah today how there's a gap in the US in our ability to fabricate devices. There's a gap between university clean rooms, like where my students work sometimes, where things get kind of strange often, and the big fabs like a TSMC, where they won't touch quantum fabrication because the volume's not large enough. There's a gap in the middle in an R&D fab that can do small volumes, work with companies like IRIQ, work with companies like Colab, and rapidly iterate to generate the technology. So what programs or policies can we create to support the development of those kinds of, those kinds of industries in the United States? All right, finally, we heard over and over again how the importance of reauthorizing the NQI Act. The NQI Act was incredible. It really drove a big investment in the United States in this research area and in development of the technology. And now is not the time to take your foot off the gas, right? Now is the time to go faster. That can come in the form of grand challenges. What devices can we make? What investments by the federal government will drive that forward? But I also just want to highlight here today the importance of funding research and discovery science. If you go back to Mark Saffman's talk and you look at all the technologies that he showed, those all started in university labs for the most part. If you come visit us at University of Illinois, we'll show you the first MRI machine that was developed there, and it's sitting now in the Beckman Institute. Those discoveries, that discovery science will take us places we don't always know and is the foundation of all this new technology. So that is really important. And the other way that federal funding of discovery science is so important is it generates that workforce of the future. If you look at where did people like me or people like Nadya come from, we came from research labs at universities where we were challenged with the hardest problems to solve, and it sharpened us into really awesome scientists and engineers. So let me just leave you with those thoughts, wrap up. I think we have about 20 minutes now, and there are 25 minutes in this room, and I think Nadya will close out. Thank you.
Okay. Thank you so much, Brian, for those really great insights. And thank you again to all of today's speakers and participants for sharing so much wisdom, your vision, your understanding, and knowledge about where we might go in the future, what our opportunities are, what the challenges are, and really why this is, as we said at the beginning, a Sputnik moment for quantum. We are in the United States leading in quantum. It is our moment to make sure that we continue to lead, that we continue to collaborate and invest to make sure this technology not only succeeds in the future, but succeeds here. So with that, I now invite you to stay for coffee, tea, and cookies. I see them here. And to continue the conversation during an informal reception right over here. On behalf of the University of Chicago and all of our partners, thank you so much.